Okay, so to proceed, let me do the following. So I want to look at d rho, and I'm going to look at d alpha zeta beta minus zeta beta minus d beta zeta alpha. Sorry, let me get a bit of space here. Insert space, good. Okay, and now I'm going to rewrite this slightly. Okay, so I'm going to write this as d alpha d rho zeta beta minus uh, d beta zeta rho minus d beta uh, d rho zeta alpha minus d alpha zeta rho. So why are these two equal? Well, look at this term over here that I've called 1. This is d alpha d rho zeta beta. This is d alpha d rho zeta beta. So that term appears there. Now look at this term in blue that I've called 2. This is d beta zeta. This is d rho d beta zeta alpha. And now this term over here is d beta d rho zeta alpha. So those two are equal. So we've got these extra two terms. But notice that the first term is minus d alpha d beta zeta rho. So we'll call this term 3. And then we've got minus times a minus is a plus d beta d alpha zeta rho. So if on the first line we had 3, on this line we have minus 3. So that those two terms sum to 0. So that's why these are equal to each other. And now what I'm going to do is I'm going to use the killing vector equation to rewrite that term and that term. So let's do that. So this will be equal to, it is d alpha, and then on the right-hand side of the killing vector equation, we have got 2 over d dot zeta eta rho beta. So that's from the first term. And then from the second term, we've got minus d beta. We've again got 2 over d. We've got d dot zeta. And then we have got eta alpha rho. Okay. And now what I'm going to do is I'm going to plug in the expression that we've got for the divergence of zeta, uh, written above in a black box. So what is this equal to? Well, the divergence of zeta has a minus, so I'll have a minus. The 2 will be left behind, but the d dot zeta over d, well, the d's will cancel. We'll have a 2 b dot x plus lambda, and then it will be times by eta rho beta. Then we've got minus. The divergence is again negative, so times by this minus, we'll get a plus. The 2 will be left behind. We will have a 2b dot x plus lambda, and then we will have an eta alpha rho. Good. Sorry, guys. I left something pretty crucial out. So let's just put these in. What I left out, you probably already noticed this, is that the first term, I should be taking a derivative with respect to alpha. So let's just move this over a bit. Good. And in the second term, I should also be taking a derivative. In the first term, I should be taking a derivative with respect to alpha. And in the second term, I should be taking a derivative with respect to beta. So if I take the derivative of the first term, d alpha will act on the lambda to give me 0. D alpha will act on the eta rho beta to give me 0. So the only term that it hits is this b dot x. When I take a derivative d alpha on b dot x, well, d alpha on b dot x is nothing but b alpha, okay? So that's the equation I'm going to be using now. So 2 times by 2 is 4. It's negative. And we've got b alpha, and we've got eta rho beta. So this comes from evaluating that term over there. And then I've got plus 4b beta eta alpha rho. And that comes from evaluating this term over here. And remember what this is equal to. This is d rho of d alpha zeta beta minus d beta zeta alpha. Well, I can now very easily integrate this equation. So I'm now going to say, what is d alpha zeta beta minus d beta zeta alpha? So what is this equal to? And the trick behind the integration, well, the obvious fact behind the integration, maybe I should say, is that we know that the alpha x beta is equal to eta alpha beta. So this is a constant, but we've got these etas. They involve a rho in them. So we can easily write down what we have to differentiate to get those two. So for the first term, we would have minus 4 b alpha, and we would have an x beta, and then we would have plus 4 b beta, and we would have an x alpha. So obviously, if I differentiate this d rho, I will get the line just above. The only extra thing that I must add in, let me not forget that I could add in a constant omega beta alpha. And the other thing that I should note is the left-hand side is anti-symmetric under swapping alpha and beta. So this constants that I add in must also be anti-symmetric. So omega beta alpha is minus omega alpha beta. Good. So now I have integrated to get what is d alpha zeta beta minus d beta zeta alpha. So that looks great. Let me just rewrite this a little bit. So, sorry, in fact, I'm going to put a 2 here. It'll make things slightly simpler, and you'll see why in a moment. Let me write down an equation for 1/2 d alpha zeta beta minus d beta zeta alpha. So what is this equal to? So I just need to multiply by 1/2. It will be minus 2 b alpha x beta, and then it will be plus 2 b beta x alpha, and then we'll have plus omega beta alpha. Good. Now, why is this a nice quantity to look at? Well, let's look at d alpha zeta beta plus d beta zeta alpha. This is an easy quantity to calculate. Why? Well, it follows immediately from the Killing vector equation, the equation at the top of the slide, and we know the right-hand side. We know what d dot zeta is equal to. So d alpha zeta beta plus zeta d beta zeta alpha is just 2 d dot zeta over d times by eta alpha beta. And let me just plug in what we know is the value of the divergence. So this will be minus 2 b dot x plus lambda eta alpha beta. All that I did was I used the Killing vector equation, and then I used the fact that I know what the divergence of zeta is, d dot zeta is. And I just plugged it in there. Now what I want to do is, I don't actually want this quantity, I want 1/2 of this quantity. So if I multiply by 1/2, I need to divide by 2 there, and I need to divide by 2 there. Now, what is so nice about having these two quantities? Well, if I add these two equations, so you can see if I add this term over here, to that term over there, adding them, what do I get? I get d alpha zeta beta is equal to, and now let me add up the right-hand sides. So I'll have minus 2 b alpha x beta plus 2 b beta x alpha plus omega beta alpha. And then let me add up this right-hand side at the bottom here. We've got minus 2b dot x plus lambda times by eta alpha beta. And now to get my conformal killing vector, I'm just going to integrate this equation. So this equation in the red box, I'm not going to try to just integrate this equation. And it's pretty easy to do it by inspection. So now we'll get zeta beta is equal to. So which terms are easy to integrate? Well, the first one is, look at this omega beta alpha. If I want to get hold of omega beta alpha, what is this going to be equal to? Well, it's just omega beta alpha x alpha. So by integrating that blue term, I get omega beta alpha zeta alpha. Now let's do the next one. So which other one looks easy? Well, actually, this 2b dot x times by this eta alpha beta, this looks pretty simple. Why? What does it look like? Well, if we have minus 2b dot x, and if we had an x beta, then if we differentiate with respect to x alpha, so let's maybe do it over here, d alpha, if we have minus 2b dot x beta, what do we get? Well, the first term, if we hit this x beta, we get minus 2b dot x eta alpha beta. That's the term we've underlined in green in the red box. But this d alpha can also hit that x sitting over there. And when we hit that x sitting over there, you get minus 2b alpha x beta. So this also corresponds to that green term over there. So these two green terms combine and they integrate to the green term that I put inside zeta beta. Good. Okay, let's continue. I'm just going to erase this now. Okay, which one should we do next? Okay, well, next we can do this term. So let me maybe now go for yellow. So let's look at that lambda. Well, this lambda, sorry, let's go for the yellow. Well, there's the lambda. And for that lambda term, we just need to have a minus lambda, because there's a minus up front. And we have got an x beta. When we differentiate this with respect to x alpha, we'll get a minus lambda eta alpha. We've got one more term, and that one would come from saying b beta x squared. So by x squared, we mean x alpha, x alpha. If you differentiate this, you'll get, well, okay, it doesn't have to be an alpha there. So let me maybe change the name. Good. Let's go, I don't know, rho. If we differentiate this with respect to x alpha, we'll get a 2 x alpha down times b beta. So we'll put this side with a plus, and this integrates to give me that term. And then finally, we could have a constant. And the constant could be something like a beta. And that is the general form of our conformal killing vector. And there's a couple of things that look good. So first of all, if you look at omega beta alpha, this you would interpret as Lorentz transformations. So it would be rotations and boosts. And you know that rotations and boosts preserve the Minkowski metric. So that means that they are conformal transformations. They are giving you the original metric rescaled by 1. So they're definitely conformal transformations. We've also got a beta. This corresponds to a translation. Again, translations preserve the metric. So they correspond to conformal transformations where you've rescaled the metric by 1. So those two make perfect sense. Lambda is actually a scaling of the coordinate. And you can see this. Remember that x tilde mu is equal to x mu plus zeta mu. And if we consider a zeta mu where lambda is the only non-zero variable, then this would become x mu plus lambda x mu, which is, actually it would be minus lambda x mu. This would be a minus, and then we would get 1 minus lambda times by x mu. Just a comment now to pay attention to. I might just change the sign of this lambda. I might change the sign of some of the parameters if I want to, okay? So if I was to change any of these parameters into minus themselves, doesn't change the conformal cleavage equation. But this, you can see, is indeed just the scaling. So finally, the one parameter that we haven't discussed so far is B alpha, and this we will see corresponds to a transformation called a special conformal transformation. And we're going to see exactly what kind of a transformation that is. So what we are going to do next, we're going to do a systematic counting of the parameters that appear in our conformal Killing vector to count how many elements we have in our Lie algebra. We're going to interpret these transformations. We're going to identify the generators that generate these transformations, and we're going to compute their Lie algebra. That'll give us a pretty good understanding of conformal transformations.